We're going to start talking about nuclear chemistry. Okay, nuclear chemistry, and discuss some ideas about the nucleus. We're going to start with stability. We're going to start with the stability of the nucleus. So, hopefully by the time we're done with today, you will be able to tell me what certain circumstances lead to stable nuclei. We've talked about the nucleus and that it has protons and neutrons, but we're going to have a new term right here, nucleons. Okay, so if we're talking about nucleons, we're talking about the protons and the neutrons in the nucleus. So, we have two numbers that we typically associate with a specific element. The atomic mass number we signify with A, which is the total number of nucleons, and the atomic number, which is Z, the total number of protons. That's nothing new to us. We've been dealing with that for a while. So if I look at this, X is the element. Top number here is A. Now that top number we'll refer to as nucleons. Bottom number is Z, number of protons. Once again, this type of a symbol is nothing new to us. We dealt with those when we talked about isotopes. Okay? Now let's look right here. Just a review. Aluminum, 2713. So top number is the number of nucleons, okay, which is 27. So this tells us that 27 nucleons, 13 protons. So based on my math, that must mean that there are 14 neutrons. Okay, 13 protons, 14 neutrons equal 27 nucleons. Now, here's just, I told you before, now I'm going to give you some numbers. I told you before that when we're talking about the mass of an atom, that we take the majority of the mass from the number of protons and the number of neutrons. If you look at these numbers, a neutron, 1.675 times 10 to the negative 27 kilograms. Very little number. 1.673 times 10 to the negative 27 for a proton. 9.11 times 10 to the negative 31st. So that's electron is even smaller than the proton and neutron. Let's talk about an atomic mass unit. An AMU, I've seen it labeled. It's also just labeled lowercase u. Okay, lowercase u. So atomic mass unit, by definition, is 1/12 the mass of a carbon-12 atom. We know that carbon-12 has 12 protons, or excuse me, has 6 protons, has 6 neutrons. So 1/12 of that would be 1. So when we're looking at this, the mass of a carbon-12 atom would be adding 6 of these protons here and 6 of these neutrons here. Because this value is so small that we don't even take that into effect. On your notes, you learned something about a strong force. And this is the exact diagram I had on the video for the strong force. Now, Hideki Yukawa proposed that there was a force between protons. And he said that that force between protons was stronger than the repulsion force of the protons. We all know that opposites attract. Okay? Likes repel. So those plus charges are repelling each other. But yet they're stuck close together here in the nucleus. Why aren't they repelling? Because of this strong force. This force between protons that hold them together. Research later showed that not only was there this force between protons, there were also this force between neutrons and between protons and a neutron. So this strong force is what was helping to hold that nucleus together. The strong force is exerted by nucleons only when they are very close together. Only when they're very close together. I put this slide on there just to show you a little bit about the evolution and how we went with these protons, these subatomic particles, you know, the atom, then came the nucleus, then came the nucleon. Now, the nucleon, all right, if we look, right here is a neutron, okay? Right here is a neutron in blue, red symbols a proton. Now, they take this neutron and they broke it down and said, okay, each neutron, okay, these subatomic particles are made by what we call quarks, okay? So 3 quarks make up a neutron. So we went and said, okay, the nucleus, okay, the atom, the smallest thing. Then we said, no, 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 no. We can get smaller. We can get subatomic particles, the proton, the electron, the neutron. Now they're saying, oh, no, 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 no. We can get smaller than that because each neutron, each proton, they're made up of these quarks. Okay, these quarks got kind of, you know, original names for the 6 quarks here. Up and down, charm and strange, top and bottom. That's how they named, bless you, that's how they named these quarks. So, you know, we're at quarks in the future. What does that hold? Will there be something smaller? Will there be something smaller? I don't know. I suppose when they came up with the atomic theory, they thought, didn't they, that there's nothing, we would never find anything smaller than an atom. Now, the mass defect. Carbon-12 has a mass of 12 atomic mass units. Okay, 12 atomic mass units. It is a combination of 6 protons and 6 neutrons. Each nucleon has a mass, though, that was greater than 1. Okay, that was greater than 1. If we would pop back to that other slide, that there was a little bit, let's say 1.00 something. Remember that slide? It was a little bit more AMUs, okay? So, as I look at this, I know that each nucleon has a mass that's a little bit greater than 1. So, the mass of a nucleus is slightly less than the mass of all the individual nucleons added together. We call that missing mass the mass defect. So, if I would take the mass defect, it would be equal to the total mass of the nucleons minus the mass of the nucleus. Okay? The mass of the nucleons minus the mass of the nucleus. That is called the mass defect. That slightly less, the amount of slightly less mass of the nucleus than the total of all 12 of those nucleons, the mass defect. Now, what's the big deal? What's the big deal about the mass defect? Okay, well, let's talk about Einstein. Okay, Einstein came up with a chemical equation, okay, in which energy and mass can be interconverted. Anybody know Einstein's equation about energy? Yeah. E equals mc squared. Yes. E equals mc squared. Energy, mass, what's the C? Any idea? You've heard of E equals mc squared. What's C? Well, C is the speed of light. You know anything about the speed of light? It's pretty fast, I would agree. The speed of light is pretty doggone fast. So, when we pack these protons and neutrons together into a nucleus, some of the mass is converted to energy and released. Okay? Remember, we just said mass defect, that if we add up all the nucleons and the mass of the nucleus, we have a mass defect. Well, that energy, that mass is converted to energy and released. Okay? The amount of mass is equal to the force of attraction holding the nucleons together. Thus, a small quantity of mass is converted into an enormous quantity of energy when we have the formation of nucleus. Why? Right here is the value. The speed of light is 300 million meters per second. That's a pretty big number, isn't it? That's a pretty big number. So, if we put in a very, very small m and times it by this number squared, can you see how that's a pretty big number now? Even with the teeny amount of mass. Even with the really, really, really small amount of mass, we're multiplying it by 300 million squared. So that's going to make the smallest amount of mass release a big amount of energy. A big amount of energy. We know that the number of neutrons vary, don't we? That's what gives us our isotopes. We talked about carbon-12 and carbon-14. We talked about the different isotopes of chlorine in your isotope lab. We've talked about the different isotopes of hydrogen. We know that the number of neutrons in a nucleus can vary. Now, the amount of instability of the nucleus is because of too many neutrons or too few neutrons. We have too many neutrons or we have too few neutrons. That creates the instability. A stable nucleus will not decay spontaneously. Okay? However, an unstable nuclei has probability to decay. Now, what does all that mean? What does all that mean to us? We're going to talk about now predicting the stability of the nucleus. All right? And one way to do this is to compare the number of neutrons with the number of protons. If I show you this diagram is, each red dot is a stable nuclei of an element. Okay? You can't read them right here. Okay? But this little dot right here is zirconium. This little dot up here is tin. Okay? This little dot up here is mercury. This whole band here, this little red band here, is what we call the belt or the band of stability. That's where the nuclei are stable. So they took every stable nuclei on the periodic table and they plotted it on this chart, and this is the band of stability. Okay? The band of stability. This right here is the number of neutrons on this axis. This axis is the number of protons. All right? So, when I look at this red line here is the line that has a 1-to-1 ratio. So that red line is a 1-to-1 ratio between the neutrons and the protons. So, for lower elements down here, the lower elements, can you see that they are on that line? So for lower elements, their nuclei are stable when they have a 1-to-1 ratio. A 1-to-1 ratio. Now, when I get up here, are the larger atomic number elements on that 1-to-1 line? Are they on this line right here? No, they're up here. So, the larger elements have a stability at more in lines of 1.5 to 1. Okay, right up here, mercury, 1.5 to 1. Right here, tin is a 1.4 to 1 ratio. Right here, zirconium is a 1.25 to 1 ratio. So their stability is greater than that 1-to-1 ratio. Okay, they're greater than that 1-to-1 ratio. Now, this only goes to 80 because when we get over 82, on the periodic table, they're not stable elements. Okay, they don't have nuclear stability when we get that high. Okay, so basically, how are we relating whether a nucleus is stable or not? What are we comparing? What are we comparing to determine if it's stable or if it's not stable? Yeah, the ratio of the number of neutrons to the number of protons. Okay, excellent.